In these videos, we're going to look at the second type of improper integrals, those that have an infinite discontinuity either at one of the limits of integration or somewhere in between the limits of integration. So you guys went ahead and you explored with your calculator, you found the values of these integrals, and so just give you a chance to check right now. You may have less decimals than I have, but as long as you have at least 5 if the value of the integral goes to 5. What do you think the value of the integral equals? Well, as suggested by these numbers, I know that they are increasing, but I don't think they're going to increase enough to where it's going to go to infinity. My guess is that the value of the integral is 1.5. And if we reach a specific number, then we say that the value of the integral converges. So this would be a convergent integral. All right, let's take a peek at what you guys got for the answers for these next 3 integrals. The numbers are certainly increasing. They're getting quite large, so I would say that the smaller that this lower limit becomes, the closer to 0, where we have that vertical asymptote, I would think that the value of the integral is approaching infinity. And if the value of the integral is approaching infinity, then we're going to say that that diverges, that integral diverges. So at the bottom of the page here, they're asking us to sketch the graphs of each of the previous functions, shading regions represented by the integrals, and trying to consider why these integrals are going to give such different results. And we've got some hints as far as the window setting on our calculator. So I'm going to graph this first function, 1 over x to the 1/3, 1 over cube root of x, or x to the negative 1/3, on the first window setting here. So we'll take a look at what that looks like. So we do know we have a vertical asymptote at x equals 0, because this function would be undefined. Okay, so what I'm seeing for my screen based on the window setting of negative 0.1 to 1, this is only 1 here, this is a negative 0.1, and then from negative 0.1 down here up to 10. I'll just say this is 10 here. So we know we have a vertical asymptote. It's going to be kind of hard to draw. Okay, but it looks something like this. Okay, so I'm going to shade the region represented by the integral. Looking at the limits here more closely, I only want to consider the region from 0 to 1. Okay, so here's x equals 1 from 0, so I'm coming back this way and collecting, accumulating this region right here. Well, I know that vertical asymptote continues upward, so there's going to be this small little region in here, not much, as that asymptote, as that graph approaches that asymptote. Okay, so we're talking about this region. Okay, so then I'm going to graph on the next window setting. So the x setting is the same as the y setting that changes. So negative 0.1 here to 1 here. Okay, but when you graph it and it's gone up to 50 on a y max, okay, the graph is quite low. And it almost looks like the graph starts on the y-axis, but it doesn't, because we do know that that's an asymptote, and there's limitations with the calculator. The calculator can't continue to draw the asymptote. The pixels are too fat. Okay, so our graph almost looks like it starts on the y-axis, but again, like I said, it does not. It's pretty short, so I'm going to start it about right here. And it goes off this way. Okay, but it continues up as x values get closer to 0. Okay, we do know that there's an asymptote. It's just too difficult to see. Okay, so when we take a look at the comparison between here and here and here, and we look at the area under the curve from 0 over to 1 only, okay, you can kind of see that it's so low here that area is going to be leveling off to 1.5. So that makes sense that this would be a convergent situation. Looking at our second graph, x raised to the negative 1/3 on the same 2 window settings as well. Okay. For this first window setting, it almost looks like the graph is just dropping in over here and coming off here. And remember, this is 1, and negative 0.1's over here, and we're up here at 10. That was my window setting. And then I guess negative 0.1 down here. Okay, so we're to consider the area from 0 to 1. So we're talking about all this space in here, and it's very clear that this is a lot more space here than on our previous graph that we had, x to the negative 1/3. Actually, this is x to the negative 3. This exponent is x raised to the negative 3. Boy, I could make myself look good and stop this and edit it, but boy, that just takes time. So x to the negative 3 on that first window setting looks something like this. So let's take a look at what happens when we change the window setting and we go up higher. Same x's. Now the graph is just up a lot higher. It went from 10 to 50. Okay, but it's not really approaching the y-axis, the asymptote, as quickly as this one did here. This one came right off the y-axis, this asymptote did, but this one is just taking its sweet time getting closer and closer to the y-axis. It comes down, it drops on your screen something like this and comes over. Okay, something like that. So again, we're trying to consider this region from x equals 0 to 1, so we're looking at all this area right here. So this graph is quite far away from the y-axis in comparison to this one right here, so that probably contributes to the I know it contributes to the reason why we have a divergent integral, why that area approaches infinity. So kind of a neat graphical representation of these integrals. Okay, so now we're going to move into how do we evaluate these improper integrals in the next few examples. Evaluating these types of improper integrals is a little bit more difficult, a little more tedious than it was when we had infinity in one of our limit positions or even both of our limit positions. Okay, so let's just kind of work our way through this one. We know it's improper because we've studied the function, and we know when x is 0 we have a vertical asymptote. So it's improper, so we're going to make it proper. The 0 is the problem, so that's a lower limit position. So I'm going to approach, A is going to approach 0, and we have to think about the direction because that's going to actually matter when we go do our calculations. So I don't want to just say A approaches 0, okay, because look at my limits here. My limits go from 0 to 1. These are my x values from 0 to 1, and you think about the graphs we just had. Okay, I want to approach 0 from not the left of 0, because that's going to put me to the left of the y-axis. I want to approach 0 from the right. So I'm somewhere in between 0 and 1, and I've got to come back and approach 0 from the right direction. And we use the plus sign to indicate that. So these are a little more difficult because we have to consider when we approach that c value, are we approaching it from the left or from the right? Okay, so this is our A and 1. And getting ready for integration and the reverse power rule, I'm going to pull that denominator up. And I'm ready to do the reverse power rule, so I can drop the integral symbol, increase the exponent to 2/3. Dividing by 2/3 results in 3/2 x to the 2/3. Using our bracket to place our limits. Now let's evaluate at 1 and A. Oh, let me get not the integral, the bracket. Actually, with the 3/2, I think what I'm going to do is I'm going to actually pull that out front. I'm going to get that out of the way, and I'm going to put it in front of the limit. So it's 3/2, limit as A approaches 0 from the right. Okay, and I'm going to plug in 1 and A for x. So I'm going to have 1 to the 2/3 minus A to the 2/3. Wrapping around down here, I have 3/2 times the limit as A approaches 0 from the right. Okay, and this expression here is just 1 minus A to the 2/3. So now I'm ready to apply the limit. So I have 3/2 times, okay, since I am going to plug in 0 now for A to the right, I can drop the limit. So I have 1 minus As I approach a 0 from the right, go ahead and just plug in 0 and see if it works. See if we don't have to do too much thinking here. Well, 0 raised to the 2/3 is just going to be 0. So this is just 1 minus 0. So my final answer is just 3/2. Let's look at this next example here. It might be worth my saying before I do that, this was the previous example here, and we did get 1.5, so it does confirm with what we saw graphically. Thinking about the previous example that we looked at too, this was one of them, and this was divergent. It approached infinity, so at least I know what my answer should be. Alright, so now we have to look at this integral. Don't just jump right into it and evaluate it. It does take some looking at and making sure that these limits are okay with this function, which these limits are not okay because our left limit of 0 makes us have an undefined situation. So let's rewrite it as a proper integral. So I'm going to approach 0, and I'm going to approach 0 from the right because I'm in between 0 and 1, and I'm coming back to 0. I'm to the right of 0, if I'm in between 0 and 1. Preparing it for integration. Reverse power rule, increase the exponent to -2, divide by -2. Evaluating from a to 1. A little bit of cleanup here before I actually plug in the limit, or apply the limit, I should say. I see this as -1/2, which I'm going to pull out as a constant multiplier, so -1/2 times the limit. Okay, and then also now that I've pulled out the -1/2 constant multiplier, I'm going to rewrite this as 1 over x squared. I'm not a big fan of negative exponents when having to calculate. Okay, I'm going to come down here since I have the room. Alright, so plugging in 1, I'm going to get 1 over 1 squared, or just 1. Plugging in the lower limit of a, 1 over a squared. Ready to plug in the limit, or plug in the 0, I should say, evaluate the limit, so I can drop the limit statement. So I've got the -1/2 times, well, that's just going to be 1 minus 1 over, okay, and if we think about plugging in 0, we're going to get another undefined situation. Okay, however, okay, we're going to come off of 0 now and just think about numbers that are close to 0, but are to the right of 0, like 0.1 is close to 0, 0.01 is close to 0, 0.001 is close to 0, 0.00, etc. is close to 0. And if we think about what's happening here, as we plug those values in for a and square them, they're going to be positive small. And positive small, very, very small, in the denominator with 1 on top is going to give us a very large number. Okay, so right here, this is just, I'm just going to put large. Then actually 1 divided by that, actually this is going to be very small right here, but the value of the fraction is going to be very, very large. So -1/2 times 1 minus infinity. So going back here, because that's the tricky part of it, is I plugged in very small values here, I squared it, they're even more small, so 1 divided by small is going to be super large, and that's why I put infinity. Okay, so cleaning this up, 1 minus infinity is just negative infinity, so -1/2 times negative infinity is just going to be a positive infinity. And that's what we saw happen graphically on the previous page, that the numbers were increasing without bound. So this is a divergent integral. So we'll take a look at these remaining examples in the next video.